The null of A, what's the definition? Set of all x's such that ax equals 0. It's all the x's, all the vectors that get sent to the 0 vector via the transformation ax. So that one's A. And so the column space of A is the span of the columns of A, the set of all the linear combinations of the columns of the matrix A. All right, so the column space of A, if you know the definition, it's linear combinations of the two columns. If you take a linear combination of these two, what space do you land in? R3. Any linear combination of these two vectors is going to be a 3-entry vector, so it's part of R3. And then the null space of A is a subspace of R2, right? So it's all the vectors that you would multiply by this matrix by to get 0, 0, 0. Yeah. So these guys just have 2 entries because you would multiply each row times that column vector can only have 2 entries. So this one's R2. Okay, so we're gonna look at section 4.2 today, learning about null spaces and column spaces of a matrix and how they relate to a matrix transformation T. So this picture is basically my notes on the reading. Okay, so this is the picture I came up with based on what the book had. So I used clouds because this is space. So I don't know if that makes any sense to you. These are spaces, so I put them in the clouds. And then we have some transformation T that takes a vector x and sends it to ax. So we've got some transformation T where x just gets multiplied by a and you land in a new space. So the domain of this transformation is Rn. So A is an m by n matrix. So Rn is the inputs. Rm is the codomain. Everything that comes out of this transformation is in Rm. And so we have the domain and the codomain. A subset of the domain is the null space. The null space are all the vectors from the domain that get mapped to 0 in the codomain. And the column space of A is a subset of the codomain, and it's actually the range of T. It's a set of all things that you can get out of the transformation. Okay, so the null space is a set of all vectors x such that ax equals 0, all the vectors that get mapped to 0 by the transformation ax. And the column space is a set of all linear combinations of the columns of A, or the span of the columns of A. Think of the column space as the range of the transformation x goes to ax. Both the null of A and the col of A are subspaces. The null space of A and the column space are subspaces. So they're vector spaces. To show that, I'll show their subspaces in a second. They're definitely subsets because they're within, right? The null of A is a subset of Rn, and the col space of A is a subset of Rm. So they're definitely subsets of known vector spaces. So there's just those 3 things you have to show that they are subspaces. So let's just quickly do that. We'll show that the col of A and the null of A are subspaces. So let's look at the null of A, and then we'll go back to the notes. So if I have 2 vectors in the null space of A, u and v in the null space, right? So if u and v are in the null space, what does that mean? It means those times A equals 0. They get mapped to 0 by the function ax. So AU equals 0 and AV equals 0. That's what it means to be in the null space. It's a definition of the null space. Okay. So what if I did A times U plus V? Does that get mapped to 0? Yeah, how do you know? Yeah, because Rn is the domain, right? Yeah. Rn is a vector space. We have all the properties of a vector space apply here, right? So I can say, I can distribute that A. AU plus AV is 0 plus 0, 0. So I have two random vectors in the null space. Their sum is also in the null space. So I've shown that closure property under addition. So that's one thing I've shown. I have to show the scalar property, right? I have to say if I do A times CU, I can use the associative property here, and you can pull the C right out. This is C times AU. That's one of the properties of a vector space. And so that's C times 0, which is 0. So if I take any scalar multiple of U, it also goes to 0. So it's also in the null space. And then what's the third thing you have to show something's a subspace? To show the closure under addition, right? For any two vectors in the space, their sum has to be in there. The 0 has to be in there, the 0 vector. So is A times the 0 vector, will that always give you the 0 vector? Yeah, because you're going to take every row of A and multiply everything by zeros, you're going to get a 0 vector out. Check, check, and check. So the null of A is a subspace of Rn. You can do a similar argument for the call space of A. I won't go through the whole thing, but you just have to show these three things, and it's fairly easy to show. So both the null of A and the call of A are subspaces. Null of A is a subspace of Rn, right, because it lives in the domain. And call of A is a subspace of Rm because it lives in the codomain. The null space of a matrix is also called the kernel of the associated transformation that sends x to ax. And sometimes we might talk about linear transformations that don't use a matrix. We did one last class in the examples. So in that case, we only call it the kernel, but it's the same thing. It's a set of all things that get mapped to 0. The null space of A is just the 0 vector, if and only if the equation AX equals 0 has only the trivial solution. And that was also the criteria we used to determine if the columns of A were linearly independent or that the transformation was 1-to-1. So if there's only one vector that goes to 0 and it's the 0 vector, the null of A is just the 0 vector. The column space of A is all of Rm, right? So if you go look at this picture, the column space of A is a subset of Rm, and it is actually the entire cloud Rm if, and only if, Ax equals B has a solution for every B in Rm. And that was the definition that we used for saying that the columns of A span Rm, or that the transformation maps onto Rm. Okay, so that's a definition we've looked at before. We're just giving it another new name. Okay, so let's look at this matrix. We've got a 2x4 matrix. Is 1, 4, 2, 2, 5 in the null space of A? Yeah, how do I figure it out? Yeah, so I just multiply. I just have to say this is some vector x, right? Or maybe we'll call it u. U equals that. So if AU equals 0, then yes, right? If not, then no. So I just do my multiplication. Times this 4 by 1 vector So this is a good chance to remind yourself how matrix multiplication works. Take each row times the vector, and my resulting answer is going to have what dimensions here? 2 by 1. Yeah. Yeah. So this vector is 2 by 4. Sorry, that matrix is 2 by 4. This vector is 4 by 1. Since the inner dimensions match, that means you can multiply them, and the result is going to have the outer dimensions, 2 by 1. 2 entries, 2 rows, 1 column. So you get those entries by taking each row times the vector. So I have 0 times 1 plus -1 times 4 plus 2 times 2 plus 0 times 5, and 1 times 1 plus 1 times 4 plus 0 times 2 plus -1 times 5. And that's 0, 0. So my answer is yes. A times that vector gives the 0 vector, which means that that vector is in the null space of A. That's the definition. It gets mapped to 0, then it's in the null space. Is 1425 in the column space of A? How can you answer that so quickly? The wrong dimensions, yeah. The column space of A is the set of all linear combinations of the columns of A. If you take a linear combination of those 4 columns, you get something in R2, right? You just do different weights on these columns and add them up. You're going to get a 2-entry vector. So there's no way this thing's in the column space. Get the wrong dimensions. Column space of A is a subset of R2. That's subset. You can also read that as a big C, like is contained in R2. All right, is the vector 3, 7 in the null space of A? Right, yeah, say that, be a little more specific, say that again. The dimensions don't match, yeah. Things that are in the null space are in R4, right, like you saw in part A. The only thing you can multiply A by is a 4 by 1 vector. So you can't multiply A times 3, 7. It's definitely not going to get mapped to 0. Okay. So you could say no, because the null of A is contained in R4, right? This guy's in R2. The null of A is a subset of R4, so it has to be a 4-entry vector. Is 3, 7 in the column space of A? Maybe. How do we figure it out? Row reduce an augmented matrix. I want to know, is 3, 7, can 3, 7 be written as a linear combination of those 4 vectors? So I could write a vector equation, just throw some weights on those columns, set it equal to 3, 7, but that would be equivalent to an augmented matrix that I could just row reduce. So I would do A augmented with 3, 7, and let's go ahead and do that on my calculator. Okay, so this was a 2 by 4, but I'm going to make it 5 so that I can augment it. All right, and then my entries. 0, -1, 2, 0, 3, and 1, 1, 0, -1, 7. All right, so it row reduces. Is it a consistent system? Yeah, it's consistent, which means it has a solution, which means yes, it's in the column space. I can write 3, 7 as a linear combination of the columns of A. It just needs to be consistent, just needs a solution, and that will mean that yes, I can write it as a linear combination of the columns of A, which means it's in the column space. Good so far? Okay. Okay, so here we've got another matrix A. It's a 4 by 4. So I want to find an explicit description for the null space of A, right? So I want to describe all of the vectors in the null space. So somehow I want to tell you what vectors live in there, all of the vectors that get mapped to 0. So I have A times what? Like what vectors here? x1, x2, x3, x4 get mapped to 0, 0, 0, 0. Like what are those vectors that get mapped to 0? How could I figure out what x's go to 0? Just throw the zeros on the end and row reduce, and I'll have a solution. And the solution to this equation is the null space. Yeah, the set of all x's that get mapped to 0. Set of all x's such that ax equals 0. So I just have to solve this thing. So go back into matrix, edit, 4 by, I need a 5 so that I can augment it. And then 0, 1, 4, 3, 0, 5, 0, 0, 1, 0, and 0, -2, -8, -6, 0. All right, so there's my row reduced matrix. Okay, so how can I describe the solutions, right? The solutions to this matrix equation. How do I do that? Yeah, I could do parametric vector form. I could say, well, let's see, x1 has to be 0. x2 plus 4x3 is 0. x4 is 0. And what are my free variables? x3. So I just have to take this equation and rewrite it in terms of the free variable. Didn't really give you enough space here. So my parametric vector form, right, my solutions, I write with a weight of the free variable. And then in here, I would put in x1 is always 0. x2 is -4 times x3. x3 is free, so I put a 1. Right? And then x4 is always 0. So that is the set of all vectors that are in the null space of A. All the vectors get mapped to 0 are a multiple of 0, -4, 1, 0. How could I write that using the word span? No. Good try. Set of all multiples of that vector, that's the span of that vector. That is the span of 0, -4, 1, 0. Yep, that is the null space. The null space of A is equal to the span of that one vector. Every scalar multiple of that vector gets mapped to the 0 vector. I should write that. Equals the null of A. So give me one non-zero vector in the null space of A. Zero, -8, 2, 0. Good. So you just took a multiple of that vector, you used 2 as your weight. Good. Okay, so we were able to describe the null space of A by solving the equation AX = 0, and all of the solutions to that equation are the null space. Okay, now I want to find an explicit description for the column space of A. So remember, the column space of A is a set of all linear combinations of the columns of A. So this one is a lot easier. It's just the span of the columns. And my columns are 1, 0, 5, 0. 0, 1, 0, -2. 0, 4, 0, -8. And 0, 3, 1, -6. That's just the definition of the column space. The span of the columns of A. So writing a description of that space is much quicker than writing a description of the null space. If I want to find a non-zero vector in the column space of A, 1, 1, 5, -2. How'd you get that? Added the first two vectors. So take a weight of 1 on the first two vectors and 0 on the second two. Add them all up. 1, 1, 5, -2. Any linear combination of those four vectors will be in the column space. So there's basically two things that you can be asked about here. Given a vector, I could ask you, is it in the null space? Is it in the column space? Or I could give you a matrix and ask you to describe the null space, describe the column space. So that's what you're going to do in your group activities. Good observation. Because the columns are linearly independent, we say that the columns of A span R4. So we could, a simpler way of writing an explicit description of the column space in this case is all of R4. Okay. You guys don't have to listen to me. I'm fixing the video. Actually, you should listen to me. So the span of these four vectors is actually not all of R4, right? Because we had a free variable, the free variable tells you that the columns of A are actually linearly dependent, which means that they do not span R4.